So today, before means proceed further with our current discussion, I would like to discuss something that is slightly different than what we were discussing. That is our differentiability of solutions, and also it is known as another part of it is sensitivity equations. The idea was somewhat simple, and we have already studied it. Like, means how parameter variation, certain parameter variation. If you go back to lecture number 18, you will find that I have shown a kind of tube type structure around our nominal solution. Like, if nominal solution or trajectory is a line, obviously trajectory will be a line, maybe a straight line or a curved line, whatever. So a curved path in your n-dimensional plane, then around that path we can have a tube type structure that means that tube type structure gives us a bound or some estimate of uh, like how much your in practical case how much your uh, any other trajectory can differ from your nominal trajectory. That type of things were discussed there. However, means at the beginning I had a notion that I could drop it, but then I think that instead of dropping this, I should consider this in my lecture also, that sensitivity equation. Why? Because later on, when you will be dealing with problems of robust control or adaptive control, you may find, obviously, whoever will teach it, the concerned professors will definitely discuss it in their discussion and in their uh, uh, like they will have their own way of describing this. But I think this discussion will some way help you to understand that notion. What is that? What we know that for a non-autonomous system, we already know that solution is written by x dot is equal to f of t comma x comma lambda, sorry, not lambda, t comma x. This is for a fixed parameter non-autonomous system. But when you have fixed parameter, it may be fixed parameter, but you have a certain uncertainty about your parameters. Like, parameters may be something you are not means sure of that, right? uh, like in future you will more get to know more about it when you have a dedicated course on robust control, like where this just let me tell you two situations and you will be able to understand that how an external disturbance can impact our system, or how a system for which you have designed your controller, or for which you are expecting something from that system, and maybe you are ready to provide some uh, means control aid like controller, uh, you are ready to couple with that system, but that controller was designed based on a nominal model of that system, but in reality it may vary. Like, if you take for an example, you can take the idea of, although that is not means in reality it not cause that much problem, but you can try take that example to understand. Like, in case of, say, you are having an RLC circuit, so the total what can I say, that total oscillation or whatever things or means take place in the RLC circuit, that oscillation, obviously the R being only the damping element, if you change the value of R, it will definitely affect. And we know that over the time we can have a positive time temperature constant or negative temperature constant. So what will happen, like if you like positive temperature constant rheostat if you take and you operate sufficiently for certain long duration, say 10 hours, more than 10 hours, then obviously what you started at the beginning and what you have at the end, if that temperature coefficient is sufficiently high, the two resistance values that you will have at the beginning of 10 hours and at the end of 10 hours will differ from each other by a tangible amount. Now, whether you will bring that kind of element or you will avoid it, means avoid that occurrence of this situation just by uh, means just by devising your circuit by taking help of elements that are almost like having a very, say you take a rheostat or where the material used is having a very small temperature coefficient. So you may need 1 hour continuous operation to reach that kind of means or to experience that kind of tangible variation that can affect your, but it can happen. And in reality, this is very crude example. In reality, it is always the case otherwise that you can, even if you try your best possible way to ensure system that is almost operate means invariant, but it happens. So another question that you can come in your mind that like if it is parameter varying, then we have this like f of t comma x. When you are telling it, then obviously it is like we are smart enough to capture that variation by means of some empirical formula. So why should we consider this uncertainty, right? The issue here is that, my friend, it is sometimes not like you must have heard about it that uh, truth is stranger than fiction. And this truth is stranger than fiction is in that way, like whenever you are considering any fictitious things or anything, but your reality must be even stranger than that. So similarly here also, you may have empirical formula. You can also, if you go back to my first lecture, then I discussed that how actually we go for a state model. It's not like that means one system comes with a like description of its state model printed on its chest and come to us with saying that this is my state model, please operate with it. In your next semester you will have system identification course where you will learn that actually how we can extract, or rather how we can try to model some either differential equation or difference equation to just to like represent the behavior of a system in an analytical manner. And even if you try your best during your you do all possible techniques, but it is very difficult for you. In that you will study that we can have different like white box modeling that is almost impossible for any real system, where you know each and everything, like you know what will happen if you take it to say like if there is a snowfall, how that snowfall will affect your RLC circuit, even if it is outside of your house and the RLC circuit is quite in, means in almost an constant temperature region, but still you know each and every very minute details of your system and also how it's going to vary. And then you incorporate all of this information together to build a model, but that model is totally rubbish because that model you can't use anywhere. Because if you need say like 50th order an equation, like 50th order polynomial you have just have for tracing the exact time variation of your rheostat, and you wrote it in that way, and also for the other two parameters like L and C. So that who will deal with that? Now, obviously, you can say that obviously we will not go for that complication. We can cut it down. Okay, fine, no issue. You make it, you almost consider it a time invariant. There is also not a problem. No need to consider it time varying if you find that variation in time is very small. No need to do that. But there also exists a situation where you will find that there may be certain things, some changes in your parameter may take place, and like instead of tracing or writing an empirical like your those kind of variation in terms of empirical function of time, means empirical form, like when you try to write a time varying things, what you need to write, it's like something plus minus this that, so it would become a bit difficult for you. But if it like, it would be quite easy for us if we like that we do not consider time varying in that way, but we consider that our system parameters may vary, and that parameter variation we know that for this system this may be the maximum amount of parameter variation. Beyond this, uh, this system parameters cannot go. Why I am telling you all these stories and all these like lavish kind of things? Because you must feel sometimes. It is not about only just learning some mathematical tools, whether you love mathematics, whether you do not love. It's totally immaterial of that, because you are trying to, I mean, you are going to apply it on a real system, and until unless you can feel the real system, your all these mathematics and all this learning will completely be meaningless. So here, when we have a system that parameter may vary, we can have this with an assumption that f of t comma x comma lambda, this is a continuous function of t comma x comma lambda. So this is the case. Now, in addition, we are assuming that it has a first partial derivative. Why do we need so? You will get to know. X and lambda for all however, later on you can shrink this domain from Rn to any D, that is your choice. Right, where p is the number of parameter, and again let us consider that lambda 0 be the nominal parameter. So what you will have, you will have a nominal state equation like x dot is equal to f of t comma x comma lambda naught with xt naught is equal to x naught, and it will have an unique, like it will have an unique solution. Sorry, in that span of right now, uh, like from my previous lecture, if you have noticed, then you can see that for all lambda that is sufficiently close to your lambda naught or nominal values, this whole thing holds good. And the, like what we just show you by this diagram, like if we have a solution like this, then we'll have nominal solution shown by the means nominal solution shown by the solid line, and this is the cylinder due to non variation of uh, lambda. So what we can write that the continuous differentiability of this f, if you have noticed that we have already mentioned that f is having first partial derivative with respect to continuous first partial derivative with respect to x and lambda, and also it is continuous in all its argument t x comma lambda. So if that is true, then the continuous first partial derivative, it implies that like sorry, the continuity of that like differentiability of f with respect to x and lambda, that implies an additional property of the solution with respect to that lambda near your lambda naught. What we can write here is very simple thing, that is now if you take the partial derivative, so we can take the partial derivative. Uh, so for this we can take the partial derivative with respect to lambda, that is will denote it like. So where we have marked this one like. And obviously being a fixed point, x not, where we have assumed that x naught is independent of lambda, although our diagram also like which I drawn the tube shape, it need to be changed, like it can be drawn like from a point, all these lines are like these points are like that. It cannot be that cylindrical tube any further, but that diagram was also correct in that context. Like you never know that which one is your initial point, and it may happen that your period of observation it is exactly like that kind of cubical shape around your nominal solution. Anyway, and what we will have here, that is differentiating with this respect to t, we can have. So what is at comma lambda? And this one is, that is the problem. When you reach at the end of the page, so for a lambda that is sufficiently small and close to lambda naught, or lambda that is sufficiently close to lambda naught, these matrices A t comma lambda and B t comma lambda can be defined on that closed interval of t naught to t1. Hence, our that partial derivative of solution with respect to lambda x lambda t comma lambda we can define over that same interval, and this this equation what we are having here, this equation uh, this equation what I am trying to say, that instead of having our previous state equation, now you can understand that whenever you are having like so here you see that after linearization kind of things we have done and written this. So as lambda means a parameter variation that is sufficiently close to our nominal parameters, the matrix this A t comma lambda and B t comma lambda can be defined over that interval t naught to t1. Now, if you see this equation, the right hand side, oh God, this right hand side, oh, very problematic, that computer causes a hell lot of trouble. Just a minute. So on the right hand side, this equation, if you consider this one, it depends this equation. In addition, it must be noted that this one is equal to 0. So this whole thing at lambda is equal to lambda naught means when it is that right hand side of this whole thing depends only on the nominal condition, right? But when there is variation, then we can still expect a unique solution. However, this unique solution, if you do not regard the parameter variation from your nominal model, although that variation is not to a great extent, to a very nominal amount of variation is there, but it cannot be ignored or cannot be unseen. In that way, it must be taken into consideration, and only will get a unique solution if we try to understand my words very clearly, that if we take care of those parameter variations, then only we'll get a unique solution. Otherwise, it will always confuse you, like having a same model that is exactly same as the nominal model. You will get different model solution because your parameters are slightly varying from each other. However, as you yourself is rigid and not ready to consider those parameter variations in your account, rather you would like to stick to that nominal system, you are getting different solution. That is not the problem of the system, rather the problem of your conservatism, I can say, that you are not ready to consider parameter variation from your nominal model. So, in a nutshell, what we can say, what was, suppose you have three parameters L or C. Now when you are having your state equation, normally what comes in our mind that as there is two energy storing element, so we can have two state variables are sufficient to represent it. However, what we can show or we can establish that it is not the case. Rather, in case of three or more parameter variations for a system, even if there is like two state variables, if there is p number of parameters and they are varying, then you need to consider additional p number of differential equation. Now in later you will study in your next semester that this p we can have minimal module realization where we can reduce this number without losing anything, but that is a different part of the story. But for layman language you can understand that when your L or C are not obliged to maintain their nominal values, they can slightly vary from what you studied or what values you have taken for your nominal system. They can produce solutions slightly different from which you could get from your nominal system. So herein comes the consideration, but in order to get a unique solution, what is need to be done, that you need to consider RLC variation. But how are you able to get that RLC variation? The one obvious way you may suggest that make this whole thing like time varying. What is that? Like if we know the exact empirical formula how L, R and C is dependent on time, we can write it, there is no harm. But as I have discussed that how much advantageous it is or how much disadvantageous it is, we will see that instead of representing this system by means of a time varying one, it would be great to consider another p number of differential equation that only record the change in your dynamics due to variation of that p elements. In a nutshell, they are only there to register the variation of your p elements. Obviously, in that case, instead of 2, now if we consider RLC 3, then we will have 5 differential equations, 5 first order differential equations to consider, but that is not a big deal. But what it could ensure in return, like instead of considering 3 now or 2, I am now considering 5, but what it will ensure in return, that now I can have a unique solution even my system is having some parameters that are that may vary from their nominal parameter, and it is not like that nominal parameter, the variation from nominal to this actual or whatever we are having during our operation time, it can be expressed in a very good model of time variation. Rather, we can always expect that it is something that is that may not be very or may not be very smoothly expressed in form of time. Rather, what we can do is that we can find out the rate of change of parameter variation, and we may find it that rate of change of parameter variation with respect to time, that is somewhat like what we can see that means this rate of change of parameters with not parameters, rather what I can say, no, sorry, I made a mistake, but parameter variation in terms of time. Rather, we are trying to the second part of this equation, try to focus on this. what you are doing here actually, you are actually measuring the deflection or deviation from your system dynamics due to change in your system parameters, and that is not very difficult to capture. Please note that I just got a bit means like made a false statement a few minutes back. So it is not. I'm sorry that it is not the parameter time variation. I again like to reiterate very clearly. Here we are doing what? We are trying to just take the change of system dynamics due to change of any parameter, right? So what you will have here, you will have another like few parameter variation. So let me write, then rather than means giving a preach on that, let me write it. Hopefully that may help you. Like now, while considering this parameters effect or this effect of parameter variation, we can have solution that is like this one. We define it actually. So we are basically writing and this allows us to write it while so this is a very important equation. It is known as this equation itself is known as a very important one. It's known as the sensitivity function. This S of t, this equation is called sensitivity equation, and this ST, where we are measuring the change of solution with respect to parameter variation, is known as sensitivity function. Please note it, and if you have any doubt or any confusion in understanding, please get back to me. Until unless you understand this, in like for nonlinear, we don't have much problem. Only a part of converse theorem will be dependent on this. But even if you are not quite means if you find it not very handy, still you can somehow manage the converse theorem. But in your later semester, you will find it real troubling. Right. Now, what happened? We have reached again the end of the page. No issue. So, I would like to discuss a problem here. And before that, let me write the complete solution. If we have a sufficient small this like the notion of stability, you can understand now that if it is confined within a region, then you can write the main solution be like this. Right? So if you neglect the higher order terms, because the same thing we have proved it in our second lecture, that these higher order terms can always be dropped or neglected. uh, if you want, you can visit my second lecture NL2. There we have discussed about this, how this could be dropped from our discussion. So this one gives us a very important thing, like this is actually our A, and then we'll have B. While the initial conditions are like, initially there is no such variation. So now we can have an expression, and then we'll see how to handle this. This is a popular equation for a phase lock loop model. We'll see that how things actually happen in reality. So let us take an example of phase lock loop system, like x1 dot is equal to x2, where this one, it is, you can think about this way, and x2 dot is equal to minus c sine of x1 minus a plus b cos of sorry, this is phase lock loop model. Fine. Now, suppose our nominal model is something like this, that we are in a mood to simplify it to a great extent. Then your nominal model will become right. Now, this then let us calculate the Jacobian, like del f del x. In one thing you must note, that this del f del x should never be calculated based on your nominal model. Rather, you should do it based on your the empirical model that completely describe your system. If you do it on this one, then what you will get, that is very interesting. You will get and obviously another part you will have. Now, as your f1 is independent of parameter, so there will be no reflection of it. But here you will have basically what I am doing here. It is very simple. This row is like del f, del a, del f, del b, and this one is del f, del c. I am doing. Now, if you have this, then you can see that the nominal model for del f, del x is what? That is and this is for that a naught is equal to 1, b naught 0, and c naught is equal to 1. And del f, del lambda, that nominal one will be what? That will be all 0, 0, 0, and here it will be minus x2 minus x2 cos x1. How I am getting minus x2? Because if you pick up this equation, right, then if you take the second one, that is uh, del a, then obviously you will leave with minus x2. Then when you will do the differentiation, partial differentiation with respect to b, you will leave with what? You will leave with minus x2 cos x1. Then for the third one, you will leave with minus sine x1. So this will going to get. Then what about your uh, complete model? That will be what is x3? X3 is basically your likewise x5 will be in this way. So you will get this. sorry. It is actually what I just made a mistake. Like this one, we need to go back where is the definition of apes we have written. So this is our S, right? Uh, Now, how we have defined S, if you can look into it, then S is something like this whole thing defines S. That means S comprises actually del x del lambda. So therefore, what we need to consider here, like what we from where this s dot t comes, that is this one. So this is x. So if this is our s, then we this should be actually lambda is equal to, so we are defining it in this way. Then so what we will get, where all these so instead of solving that two first order equation, now you have to solve these eight first order equation. However, one advantage that you will get, like instead of only predicting the solution bound, that solution will lie inside a tubular structure that is centered around your main solution or nominal solution. Here you will get the exact solution, that uh, exact solution we can get from this, right? So this is very important observation for us. So basically the goal of this one discussion is that instead of having one, we need to have like, now obviously the question comes that if we have three states and two parameters, how many will get? Obviously for each of three means we'll have six, like the dimension of the total it, together with sensitivity equation, it will become 9, 3 for your state and means 6 due to your parameter variation, like 3 state equation and 2 parameters, that comprises the 6 equations. Now in actual case, what we can do is that sometimes we try to take help of some mathematics to reduce the number of parameters, like that kind of model reduction, we often take help of model reduction. Otherwise, you can understand that if you have total n number of state equation and m number of means parameters or p number of parameters, it is going to generate another n p first order differential equation, and that is not a like a very handy amount if you have a complicated system like having 29 states and say 19 parameters. So you can understand that how many number of additional equations will come in the picture, like 29 into 19. And you may claim, or you may means ask me that their microcontroller and all these things are very powerful. So once you write a program, you are an efficient programmer, you can manage it 29 into 19 first order differential equation. It's not a big deal, but it will become a big deal because it is not only about those equation and not only about finding the exact solution, but every steps you have to calculate, you have to feed the present state data for future stage calculation. So in that lots of issues will come, and hopefully in your digital control you have also learned that how sampling interval of system can affect, and more number of system signals you try to deal with, more chance of means error calculation, and that error may be means uh, error, there may be a accumulation of error. Now in order to means circumvent this problem, we take help of robust control, where we consider that instead of having actual solution, we rather find ourselves happy with a solution bound, and that we will be learned in your next semester. But now in our next video we will going to discuss converse theorem. Instead of dealing with exact solution, how we can means utilize all this knowledge, although it gives us an unique solution, but we will see that we will not look for unique solution, rather how these aspects of unit solution can be circumvented, and we can have a Lyapunov function for non-autonomous system. I do not know, sometimes my computer causes so much problem, I cannot stop the video. It sometimes get hanged and unnecessary. I do not want